Welcome to this walkthrough of LeetCode problem number 440, KTH smallest in lexicographical order. In this problem, we explore how to identify the KTH smallest number in lexicographical order within a given range. We'll break this down step by step, discuss key strategies, and analyze the solution's efficiency. Let's dive in. In this problem, we are tasked with finding the KTH smallest number in lexicographical order from the numbers 1 through n. Lexicographical order is similar to how words are ordered in a dictionary, where the numbers are sorted as strings character by character. For example, if we take the numbers from 1 to 13, the lexicographical order would look like this: 1, 10, 11, 12, 13, 2, 3, 4, 5, 6, 7, 8, 9. Notice how 10 comes after 1 because it begins with the digit 1, followed by the digit 0. This is the order we are working with. Now, the goal is to determine the KTH smallest number in this sequence. Let's take a look at an example to understand this better. For n equals 13 and k equals 2, our task is to find the second smallest number in the lexicographical order. Here's the explanation for the first example. The numbers from 1 to 13 arranged in lexicographical order are 1, 10, 11, 12, 13, 2, 3, 4, 5, 6, 7, 8, 9. If we count through this sequence, the second number is 10. So, the output is 10. Now, for another example, let's consider n equals 1 and k equals 1. In this case, there's only one number, which is 1. The lexicographical order is simply 1, and the first and only number in this sequence is 1. Therefore, the output is 1. These examples show how we determine the KTH smallest number for smaller values of n and k. Let's move on to a slightly larger example to further illustrate the concept. For this example, let's set n to 100 and k to 10. First, we generate the lexicographical order for numbers from 1 to 100. The sequence begins like this: 1, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 2, and so on. Now, we need to find the 10th smallest number in this sequence. By counting, we see that the 10th number is 17. So, the output is 17. This example highlights how the sequence grows for larger values of n and how we can identify the KTH smallest number within it. However, with higher values of n, the sequence becomes extremely large, and we need to consider constraints and edge cases to solve the problem efficiently. There are a few important points to keep in mind for this problem. If k equals 1, the output is always 1, as 1 is the smallest number in lexicographical order. For larger values of n, especially when n reaches 10 to the power of 9, it is impractical to generate the entire sequence. Instead, we need to traverse the lexicographical tree efficiently to directly locate the KTH smallest number without constructing the entire list. This approach ensures the solution is optimized for both time and space, especially given the constraints where n can be as large as 1 billion and k can go up to 100,000. Understanding these constraints and edge cases is key to developing an efficient algorithm for this problem. To solve the problem of finding the KTH smallest number in lexicographical order, we can consider several approaches. The first is a brute force approach, which is straightforward but inefficient for large inputs. The idea is to generate all integers from 1 to n, convert them to strings, sort them lexicographically, and then return the KTH smallest element. This involves creating a list of numbers, sorting them based on lexicographical order as strings, and simply picking the KTH number in the sorted list. While this approach is simple to implement, its downside is the computational cost. Generating the list takes n time, and sorting it based on string comparisons adds n log n. Overall, this approach becomes impractical for very large values of n, such as n equals 10 to the power of 9, due to the sheer amount of data and the inefficiency of sorting at such scales. An optimized approach to address the inefficiency of brute force is to use prefix counting with a greedy strategy. This approach leverages the lexicographical structure of the numbers to significantly reduce the amount of work needed. Instead of generating and sorting all numbers, we focus on directly counting how many numbers exist under a given prefix. Lexicographical order prioritizes smaller prefixes, so by determining the count of numbers starting with a particular prefix, we can skip over large groups of numbers at once. The process begins with prefix 1, and we calculate how many numbers fall under this prefix. If the count is less than k, we move to the next prefix and reduce k by the count. If the count is greater than or equal to k, we explore deeper levels of the prefix by appending digits and repeating the process until k reaches 0. This method is highly efficient, with the counting of numbers under a prefix taking O log n time and requiring only O log n steps for prefix adjustments, making the total complexity O log n asterisk log n. While this approach demands a deeper understanding of prefix counting, it avoids the inefficiencies of generating or sorting large datasets. Another approach worth considering is a depth-first search, or DFS, traversal of the lexicographical tree formed by the numbers from 1 to n. In this approach, each number is treated as a node in the tree, and appending digits to the number forms its child nodes. The traversal is performed in lexicographical order, visiting one node at a time, until we have visited k nodes in total. This method naturally follows the lexicographical order without the need for sorting, and it can be more intuitive to implement than prefix counting. However, its time complexity depends on the value of k, as we may need to explore up to k nodes, resulting in a complexity of k. While this is simpler than the prefix counting method, its performance can degrade for large values of k, especially when k approaches n. For smaller values of k relative to n, though, it may still be an acceptable choice. The chosen strategy for solving this problem is the optimized approach using prefix counting. This method is the most efficient for handling large input sizes, particularly when n is very large, such as 10 to the power of 9. The key insight of this approach is its ability to skip over entire ranges of numbers by utilizing the lexicographical structure of prefixes. By focusing only on the necessary prefixes and dynamically adjusting based on the value of k, this method eliminates the need to generate or sort large datasets, making it highly scalable. Its time complexity of O log n asterisk log n is significantly better than the O n asterisk log n of brute force or the O k of DFS, especially for large n. However, the trade-off is the complexity of implementation, as prefix counting requires careful handling to avoid off-by-one errors. Despite this, the balance of efficiency, scalability, and practicality makes the prefix counting approach the ideal solution for this problem, ensuring optimal performance even for the largest inputs. The problem we're tackling is to find the kth smallest number in lexicographical order within the range from 1 to n. For example, if n is 13 and k is 2, the numbers in lexicographical order are organized as 1, 10, 11, 12, 13, 2, 3, 4, 5, 6, 7, 8, 9. Here, the second smallest number is 10. Instead of generating and sorting all numbers explicitly, which would be inefficient, we use a prefix-based iterative search. This approach dynamically calculates the number of elements under each prefix, making it highly efficient with a time complexity of O log n asterisk log n in most cases. To understand this better, imagine the numbers arranged in a tree structure where each node represents a number, and its children are formed by appending digits to it. By navigating this virtual tree lexicographically, we mimic sorting the numbers and identify the kth smallest one by counting how many numbers fall under each prefix. To solve this problem, we first calculate the gap between consecutive prefixes. For two prefixes, such as prefix and prefix plus 1, the gap represents the count of numbers between them that lie within the range of 1 and n. This is done by iterating through the levels of the tree and summing up the contributions for each level. At any level L, the range of numbers under a prefix can be expressed as prefix asterisk 10 to the power of L, prefix plus 1, asterisk 10 to the power of L1. We then restrict this range to fall within 1 n to ensure we stay within bounds. By summing up the valid range sizes, we get the total gap between the prefixes. Using this gap, we can navigate the tree to find the desired kth number. Starting from the smallest prefix, which is 1, we determine whether the kth number lies under this prefix. If k exceeds the gap, we skip the prefix by subtracting the gap from k and move to its sibling. If k is within the gap, we dive deeper into the subtree of the prefix by appending a digit and reducing k by 1, since the current prefix is also counted. This process continues until k becomes 0, and at that point, the current prefix is our answer. There are three key insights that make this algorithm efficient. First, visualizing the numbers as a lexicographical tree allows us to avoid explicitly sorting them. This tree structure helps us systematically navigate through the numbers. Second, the gap calculation is dynamic, meaning we compute the number of nodes under any prefix on the fly, which eliminates unnecessary pre-computation. Finally, the traversal technique ensures efficiency by navigating the tree level by level. This keeps the complexity logarithmic relative to n. The beauty of this approach lies in its simplicity, as it primarily relies on integer arithmetic. We don't need any additional data structures, which keeps the space complexity constant. By combining these insights, we achieve a solution that balances efficiency and clarity. Let's solidify our understanding with an example. Suppose n is 13 and k is 2. We start with the prefix 1, which represents the smallest number lexicographically. Calculating the gap under this prefix, we find it covers the range 1, 9, which contains 9 numbers. Since k equals 2, the kth number must lie within this range. Next, we go deeper by appending a digit to the prefix, making it 10. Reducing k by 1, we now have k equal to 1. Calculating the gap under the prefix 10, we find it covers the range 10, 10, containing exactly one number. Since k is now 1, the kth number is the prefix itself, which is 10. This demonstrates the efficiency of the approach, as we arrive at the answer without explicitly generating or sorting the entire list. In terms of complexity, the time required is proportional to O log n asterisk log n, due to the dynamic gap calculations in prefix-based traversal, while the space complexity remains O1, as no additional structures are used. This implementation solves the problem of finding the kth smallest number in lexicographical order efficiently, avoiding the need to generate and sort the entire list. Step-by-step explanation. 1. Helper function count_steps. This function calculates the number of integers between prefix and n that share the same prefix. It expands the search range by multiplying the prefix by 10, e.g., 1-10, 100, and counts all valid numbers within the range. It stops when the range exceeds n, ensuring no invalid numbers are counted. 2. Main function logic. Start with current equals 1 since lexicographical order begins with 1. Decrement k because the search begins with the first number already considered. 3. While loop. The loop continues until the kth number is found. Use the helper function count_steps to calculate how many numbers exist under the current prefix. If the total steps is less than or equal to k, move to the next sibling by incrementing current and reducing k by steps. Otherwise, move to the next level, child, by multiplying current by 10 and decrementing k by 1, as we've moved one step deeper in the tree. 4. Return the result. Once k becomes 0, the current prefix represents the kth smallest number in lexicographical order. #keypoints. The algorithm uses a prefix-based approach, which avoids generating and sorting the entire sequence of numbers. By leveraging the hierarchical structure of numbers, e.g., 1-10-100, the solution explores numbers efficiently in lexicographical order. The time complexity is approximately O log n asterisk log n, due to the nested iterations over prefixes and their children. Here, we start with the Java implementation of the solution. The main function, find kth number, takes two parameters, n, the upper limit of the range, and k, the position of the desired lexicographical number. To navigate through the lexicographical order efficiently, a helper function countSteps is defined within the main method. This function calculates the number of steps between a given prefix and the upper limit n. Using a while loop, it expands the range defined by the prefix by multiplying it by 10, effectively moving deeper into the lexicographical tree. For each range, it adds the number of valid numbers to the steps count, ensuring it doesn't exceed n. Finally, countSteps returns the total steps as an integer. Back in the main function, we initialize current to 1, representing the smallest number, and decrement k by 1 since we are starting from the first element. The main while loop then begins, where we repeatedly calculate the steps for the current prefix to decide how to proceed. If the steps from the current prefix are less than or equal to k, it means the kth smallest number is not within this prefix, so we move to the next prefix by incrementing current and reducing k by the number of steps. On the other hand, if the steps are greater than k, it means the kth smallest number lies deeper within this prefix. In this case, we move one level deeper in the lexicographical tree by multiplying current by 10 and decrementing k by 1 to account for the current step. This process continues until k becomes 0, at which point current will hold the kth smallest number. Finally, we return current as the result. This approach ensures that we efficiently traverse the lexicographical order without generating all the numbers explicitly, keeping the solution optimal. In this example, we are tasked with finding the second smallest number in lexicographical order for numbers ranging from 1 to 13. To solve this, we start by initializing current to 1, as this is the smallest lexicographical number. Since we are looking for the second smallest number, we adjust k to 1 by subtracting 1, as the first number is already counted. Next, we calculate the number of lexicographical steps from the current prefix using the count_steps function. Starting with first and last both at 1, we count all numbers in the range 1, 1, adding 1 to our total steps. We then extend the range to 10, 19, which contributes 4 additional steps, as the range is bounded at 13. This gives us a total of 5 steps. Since the total steps from the current prefix exceed k, we stay within this prefix but move deeper into it by setting current to 10, and we decrement k to 0, as we have now pinpointed the desired range. At this point, since k has reached 0, we can conclude that the second smallest number in lexicographical order for the range 1 to 13 is current, which is 10. Now, moving on to the next example, where the range is expanded to numbers from 1 to 100, and we need to find the 10th smallest number. We initialize current to 1, as before, and adjust k to 9 by subtracting 1. This setup allows us to begin iterating through the prefixes in search of the 10th smallest number. Starting with the first loop iteration, we calculate the number of steps from the current prefix, which is 1. Using the count_steps function, we start with first and last at 1, and add 1 step for the range, 1, 1. We then extend the range to 10, 19, contributing 11 steps, as there are 10 numbers in this range. This gives us a total of 11 steps. Since the total steps from the current prefix exceed k, we determine that the desired number lies within this prefix. To explore deeper, we set current to 10 and decrement k to 8, narrowing down our search further. In the second loop iteration, we now calculate the steps from the prefix 10. Using count_steps, we start with the range 10, 10, adding 1 step. Extending the range to 100, 109, we add 1 more step for the range 100, 100, giving us a total of 2 steps. Since the total steps do not exceed k, we move to the next prefix by incrementing current to 11 and reducing k to 6. In the third iteration, we calculate the steps from the prefix 11. The range 11, 11 contributes 1 step, and this is the total for this prefix. Again, since the total steps are less than or equal to k, we increment current to 12 and decrement k to 5. The process continues as we iterate through prefixes, adjusting current and decrementing k each time the steps from the prefix are less than or equal to the remaining value of k. We explore prefixes 12, 13, and so on, until k is reduced to 0. At this point, the final value of current is 19, which means the 10th smallest number in lexicographical order for numbers from 1 to 100 is 19. For the final example, we are now tasked with finding the 20th smallest number in lexicographical order for numbers ranging from 1 to 50. We start with current initialized to 1 and adjust k to 19 by subtracting 1. In the first loop iteration, we calculate the steps from the prefix 1. Starting with the range 1, 1, we add 1 step. Extending to the range 10, 19, we add 10 steps. Finally, extending to the range 20, 29, we add another 10 steps, resulting in a total of 21 steps. Since the total steps exceed k, we determine that the desired number falls within this prefix. We set current to 10 and decrement k to 18. The process then continues, iterating through prefixes and narrowing down the range until k is reduced to 0. At that point, the final value of current is 29, meaning the 20th smallest number in lexicographical order for numbers from 1 to 50 is 29. To analyze the time complexity of this algorithm, we break it into 2 main components, the count_steps function and the main loop and the find kth number function.
The count_steps function calculates how many numbers exist between a given prefix and the upper limit n.
It does so by iterating level by level through the numbers that share the same prefix. At each level, it updates the range of numbers by multiplying first and last by 10 and adding 9. The depth of this iteration corresponds to the number of digits in n, which is approximately O log 10 n.
In the main loop, we call count_steps repeatedly to decide whether to move to the next prefix or go deeper into the current one.
Since we decrement k in each iteration, the loop runs up to k times, though it is ultimately bounded by n. Combining these, each iteration of the loop involves a call to count_steps, which is O log 10 n, and the total number of iterations is at most k. This gives us a total time complexity proportional to O k log 10 n. Therefore, the overall time complexity of the algorithm is O k log 10 n, where k is the input value and n is the upper bound. Now turning to the space complexity, the algorithm is highly efficient in this regard. The count_steps function only uses a constant amount of space to store variables such as steps, first, and last. Similarly, the main function keeps track of variables like current and k, all of which require constant space. No additional data structures, such as arrays or recursion stacks, are used. Thus, the space complexity is O(1), making this algorithm not only time efficient but also space efficient. To understand the significance of this optimization, let's compare our approach to a naive solution. A brute force method would involve generating every number from 1 to n, sorting them lexicographically, and then accessing the kth smallest number. This would result in a time complexity of O n log 10 n, due to the sorting step, and a space complexity of O n, to store all the numbers. In contrast, the optimized approach avoids generating all numbers and instead navigates directly through the lexicographical tree. This drastically reduces the time complexity to O k log 10 n, which is significantly faster for large n and smaller k. Additionally, it eliminates the need for extra storage, reducing the space complexity to O(1). These improvements highlight the efficiency of the current solution.
Now let's examine the algorithm's performance across different scenarios.
In the best case, when k is small, the loop exits quickly, leading to a time complexity closer to O log 10 n. In the average case, for arbitrary values of k, the complexity is proportional to O k log 10 n. The worst case occurs when k is close to n, requiring the maximum number of iterations and resulting in a time complexity of O n log 10 n. The logarithmic factor in the complexity stems from the depth of the lexicographical tree, which corresponds to the number of digits in n. The linear factor, k, arises from the number of iterations needed to find the kth smallest number. Together, these factors give us the overall complexity of O k log 10 n, consistent across all cases.
When solving this problem, several common mistakes can trip you up.
First and foremost is using a brute force approach for large values of n. For small n, generating all numbers from 1 to n and sorting them lexicographically may work, but when n becomes very large, like 10 to the power of 9, this method becomes computationally infeasible. Sorting alone has a time complexity of O n log n, which will exceed time limits.
Another frequent error is misunderstanding what lexicographical order means. This is not numerical order, it's the order strings are sorted, character by character.
For instance, 10 comes before 2 lexicographically, even though numerically, 2 is smaller. Misinterpreting this can lead to incorrect results. Additionally, some people overcomplicate the calculation of steps between numbers in the lexicographical tree. For example, calculating the steps between 10 and 19 can be tricky, especially when n creates boundaries that need to be respected.
Lastly, there's the assumption that k is always small.
When k is close to n, naive approaches that start from the smallest number and iterate sequentially can become highly inefficient. Optimized solutions need to handle both small and large k effectively. Ignoring edge cases is another common pitfall. For example, when k equals 1, you're looking for the smallest number, and when k equals n, you need the largest.
Numbers with varying lengths also introduce complexity, so it's crucial to test thoroughly with boundary cases. Now, let's focus on key insights for interviews.
The essence of this problem lies in efficiently navigating the lexicographical tree that represents all numbers. Each number forms a subtree, and the challenge is to navigate this tree step by step. Since generating all numbers is infeasible, optimization is rooted in leveraging the prefix structure of lexicographical order. By calculating the number of steps a prefix covers, you can skip unnecessary branches and zero in on the target. To master this, practice problems that involve tree traversal or prefix-based logic. These will sharpen your mathematical reasoning and traversal skills, which are essential here. Finally, be ready to explain trade-offs during interviews. Compare brute force, sorting, and optimized greedy approaches. The greedy step counting method is efficient because it avoids unnecessary computations, and you should be able to articulate why that's the case. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 386, Lexicographical Numbers, is a simpler version of this problem where the goal is simply to generate the lexicographical order up to n. It's a great starting point to familiarize yourself with this concept. Another related problem is LeetCode 315, Count of Smaller Numbers After Self, which involves sorting and managing order efficiently, though the context differs. LeetCode 282, Expression Add Operators, is another example that requires efficient reasoning with strings, which is an overlapping skill. Lastly, LeetCode 164, Maximum Gap, focuses on sorting and optimizing numerical operations. While the specifics vary, the underlying themes of efficient traversal and order management are consistent, making these problems excellent practice to build your skill set. Finally, let's compare alternative approaches and their trade-offs. The brute force approach, where you generate all numbers from 1 to n, sort them lexicographically, and retrieve the kth number, is straightforward but impractical for large n. Its time complexity of O, n log n, makes it suitable only for small values, such as n less than 10,000. Another approach is depth-first search, or DFS, which traverses the lexicographical tree recursively, counting steps until k is reached. This method is more efficient than brute force but may still waste time exploring unnecessary branches, especially for larger inputs. The most optimal approach is the greedy step counting method. This strategy calculates the number of steps between consecutive prefixes and uses this information to skip irrelevant branches entirely. Its complexity is approximately O log n asterisk log n, reflecting the logarithmic traversal depth and the efficiency of step calculation. This method strikes the right balance between correctness and efficiency, making it the ideal choice for handling large values of n and k. Each approach has its place, but for large-scale problems, the greedy method is the clear winner. Great job! In this summary, we reviewed the key algorithm, its complexity, and important takeaways. This problem highlights efficient traversal techniques and their applications in lexicographical order problems. Thank you for watching, and don't forget to like and subscribe for more insights. Keep practicing, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!